Mysterious great dimming of Betelgeuse, which happened about a year ago in 2020, February 2020. Now let's see, I have to continue, my meeting is being recorded. Okie doke. So I want to start back, perhaps I would say way back. Let's go back 17,000 years, because I just discovered that if you go to the Lascaux caves in the southern part of France, you will find images on the wall, and they actually mark out, as you see on the right, the constellation Orion. So while these folks weren't looking at it quantitatively, they certainly knew where Betelgeuse was and recognized it. So let me remind you what the star is. It's a supergiant. It's about 700 light years away. So what we're seeing now happened around 1300 AD. It's big, it's really big. If we took the star and put it at the center of our solar system, the surface, and this is the optical surface, would extend out to the distance of Jupiter. It's about 1,000 times the radius of the sun. Theorists believe that the mass originally, it was about a 20 solar mass star. It's probably less now because it's obviously been losing mass. It's in a core helium burning phase. And it's also rapidly rotating, which is somewhat puzzling. And there's some thought that maybe it was earlier a binary, and the supergiant took its companion and accelerated the rotational velocity. Okay, we have been looking at Betelgeuse, as Tatiana said, for a long time. Ron Gilliland and I made the first direct image of the surface of a star, which is that of Betelgeuse, using the faint object camera on HST. And there were two things that were notable from this observation. One was that the surface, in the UV surface, had a very large, hot, convective spot on the star. And secondly, the fact that the ultraviolet chromosphere extends way beyond the optical, about 3 times the optical radius is where the UV extends, and even beyond that, that's sort of the half power point. So if the surface had a convective spot, and it's the UV is very much extended. And we also followed the star for a number of years, taking images with the FOC, which unfortunately was taken off the Hubble after a number of years after launch. But you can see here in this montage the changing appearance of the star with the same exposure time. Now, the image in the upper left-hand corner is a white dwarf, HC4. So you can see a white dwarf gives us, 5 little bright pixels, and then we see on the right, and the subsequent sequence as you move along from 1 year to 2 years, 3 years, etc., how the appearance of the star changes and how the star is clearly much more extended. These are all the same exposure time, about an hour, and they're in the UV ultraviolet continuum. So we're learning, we knew a lot about the star, we know a lot about the star, and we could even learn more with Hubble subsequently, where we could take the aperture, and this was the GHRS aperture, and scan it in the pattern that you see marked by these white dots in the left panel to determine the orientation and rotation. At each one of the offset positions, we would obtain a spectrum. And from the spectrum, one could determine the radial velocity and thus the orientation and the rotation. And in the right, you see the model that, that we developed of the star at that time, which showed that the bright spot was aligned with a polar axis. In other words, that the axis appeared to be about 48 degrees east of north, and we then assumed that, well, the bright spot was consistent with the position of the pole, and that also was confirmed subsequently when infrared observations have shown plumes that appear extended from the surface of the star in the direction, at least in that case, towards the southwest. of the star. And subsequently, as technology improved, and interferometry improved, and theory improved over the years, there have been confirmation of these variable hotspots. On the left is an infrared H-band taken from IOTA, which is was our CfA's interferometer at Mount Hopkins, and you see two bright spots. Simulations show that there can be bright spots, although my understanding is they can't be simulated as large as what to the extent that have been observed. On the right, there are different epochs over 3 years showing the changing appearance of the star in the infrared. ALMA, of course, has done a wonderful job at submillimeter wavelengths. Pierre Carvella did an extensive study where he shows, and you see on the right the ALMA image, and then overlaying that the SiO, silicon oxide plumes that this time seem to come from the northeast of the star. And it suggests that maybe there was mass outflow from the northeast. There was a focused dust plume, which was polarized in that direction. Other folks have said there's a dust shell at about 1.5 stellar radii. Remember, the UV goes out to at least 3 stellar radii, perhaps more. So the atmosphere is complex, and it contains high temperature and low temperature material, probably molecules as well, and as well as strong chromospheric emission. So what's happened in 2020? Well, for 150 years, Betelgeuse has been observed somewhat photometrically, at least compared to other stars. And it was only in 2020 when it became the faintest it had ever been in 150 years. And you see these are the last 6.5 years, and you see this modulation, which is about a 420-day modulation, which appears to be a simple pulsation of fundamental mode. There are gaps because Betelgeuse goes too near the sun, generally from May through July, maybe half of August. So we have these gaps where we don't quite know what's happening, but you can clearly see that the minima are about optical magnitude of about 0.8. And then, oh my goodness, in the fall of 2019, it started making its normal trip to a minimum magnitude, but it didn't stop. It just kept going down. And as a matter of fact, in January, when we were all at the AAS meeting in Honolulu, we were all out on the balconies at night looking up, and the constellation just didn't look properly at all. I mean, it was the bright star, which is supposed to be in the shoulder of Orion, had vanished. And it reached a minimum around the 7th to the 13th of February in 2020. Okay, I had started in 2019, at the beginning of the year, a 3-year program to visit Betelgeuse, and we've actually put together a group of people, which we affectionately call the MOB, M-O-B, for months of Betelgeuse, to take radial velocity measures, optical spectra, imaging. We've been doing imaging at the VLT in Chile. There's been radio work done at E. Merlin. We had VLA observations, many things, but I'm going to focus here principally on the HST visits. And in the left, you see the last 2 cycles of the optical magnitude and the variation, and the red vertical lines show you when we visited the star. Hubble also cannot observe the star during the period when it's too close to the sun. And we didn't ask for particular times to schedule the visit to Hubble, because that then puts additional constraints on the program, and we just wanted to get as much as we could get during the time. But fortunately, we started observing it in September, the fall of September, October, and then as it started getting dimmer in December, and then back again at the end of January, February, and April. And we have continued this year, which I will talk about later. So the left panel shows you the optical magnitude and the great dimming, as we call it. First it was termed a fainting, and that was deemed not socially acceptable. So it's now the great dimming of Betelgeuse. And on the right, you see the radial velocities as obtained from Stella. I should mention that these optical magnitudes on the left came from Rich Washingtonics Observatory at Villanova, as well as a lot of AAVSO magnitudes. They were just invaluable, incredibly valuable in following carefully with photometric accuracy the behavior of the optical magnitude of the star. And on the right, we have the radial velocity, and this has been measured by Klaus Strassmayer, Tom Granzer, and his colleagues at the observatory in TA. They have robotic observatories, robotic spectroscopic observatories, and every night for 10 years now, they've been obtaining high resolution shell spectra of many stars, including Betelgeuse. And you see the radial velocity during the time of minima, or actually slightly below the time of the minimum in optical. It was moving outward at a maximum, and it had been moving outward from the photosphere. The photosphere was moving outward for several hundred days before the minimum in optical magnitude occurred. Okay, so what did we do with Hubble? With Hubble, we could take the aperture that TESS offers us of 25 by 100 milliarc seconds, roughly the size outlined by this yellow dashed rectangle, and we would move it in stop and take a spectrum at every one of 8 positions as we move. Most of the time it was from the southeast up here to the northwest. Several times it goes in the other direction, simply because of the orientation of the Hubble spacecraft. And you note here that I've shown the submillimeter image in color, the one that Carvella published. The white ring circle is the optical diameter of the star, which is about 42 milliarc seconds. And then the purple circle, the larger one, marks the UV diameter of the UV continuum, which is about 125 milliarc seconds. So therefore, we can get anywhere from 6 to 8 resolution elements as we move across with this particular aperture. So what did we find? I want to show you here in particular the magnesium-2 lines. These are chromospheric lines, very strong, and we could see that they changed quite dramatically at certain times. Now in the left panel, I'm showing the flux of the magnesium H and K lines at different positions. And from the left the left side corresponds to the southeast part of the star. That's the lower left of the star. And the right is the northwest of the star, because we recall in the previous slide that we move across at sort of a 45-degree angle. And the different points mark the flux of the H and K line at each one of these points as a function of time. And what I've done is I've marked the strong points in September, October, November of 2019 in red. And you can see that as we start in early January and March of 2019, this represents the distribution of flux across the ultraviolet image of the star. But as we move into the fall, September, October, and November, there is a huge increase in the flux by factors of 3 to 4, mainly in the southeastern part of the star. However, by the time February arrived, which is indicated by the open circles down here, life was sort of back to normal. I've also indicated here the last 2 observations which we had. We're in our 3rd year of the observations of this program with Hubble. We have 2 more observations coming up, one in about a week and another in April. But here in August and November, just about 2 months ago, it's back to the blue. Maybe August was a little high in the south, but right now in November, the star is sort of back to normal. And you can see the change in the profile on the right, where we show the March profile and the February profile are pretty similar. But in October, when that spot was very bright in the east of the star, the profile is substantially enhanced in the southern hemisphere. And the folks, the artists at Space Telescope, have a little image up here that is a artist perception of what went on, of this bright flux in the southern hemisphere of Betelgeuse. Okay, what can we learn about that? Well, you can use various spectroscopic diagnostics, one of the most, to infer the physical characteristics of this bright spot. One is the carbon-2, it's a boron atom, and by looking at the ratio of the two lines marked here, this gives us an indication of the electron density in the low chromosphere. And on the right, we show the hot spot, this red curve here marked by the red squares. And the fact is that during September, October, and November, the ratio of these two lines became much smaller. And when the ratio becomes smaller, it indicates that there's an increase in electron density. And you can see that in the center, there wasn't much change at all, but in that hot spot, there was definitely an increase over the southern hemisphere that happened in the fall. We can also look at the line profiles, and it turns out that there's been a lot of very detailed modeling of the response of an atmosphere, the spectroscopic response of an atmosphere to a traveling pulse, an impulse of outward moving higher temperature, slightly higher temperature material. And on the left, you see one of these calculations where time is running upwards and one has a magnesium line that's relatively symmetric. And then as you move on and the pulse travels through the line forming region, the blue side of the line, the short wavelength side of the line, becomes much stronger than the long wavelength side of the line. And this represents material moving outwards in the atmosphere, and then it moves out, it passes through, and then it's followed by an outflowing wind. And you can see then the asymmetry changes dramatically. Well, if we look at what we saw from the observations of Betelgeuse, we see a similar asymmetric enhancement. In other words, in the early part of 2019, things were pretty normal with a ratio in the order of 0.6. And these are the peaks of the magnesium K line. But then during September, October, November, oh my goodness, it got the ratio changed substantially. The blue side became much stronger relative to the red side, and then it decreased back to normal again. So it's a similar asymmetric enhancement as predicted by these calculations, and suggesting that indeed there was outflowing material. We think what's happened is that there was a sort of a meeting of two things at the same time, that there was probably a very large convective cell on the surface of the star. And at the same time, the photosphere was moving outwards very rapidly for a long period of time. Stella showed us that the photospheric velocity was at maximum outflow. And we also know that in February, there was increased polarization of circumstellar material. Now, at the same time, Miguel Montargues and the rest of us had obtained time on the VLT to image the star with sphere. And in January, you see the image to the right, the first image, the star appeared fairly symmetric. However, by the end of December, the southern part of the star was much dimmer. It was dimmer by about a factor of 10 from what it had been previously. So the suggestion is, one suggestion is that this material that we saw moving out in the fall moved further out, cooled down, formed dust, and the dust is what we see moving away and across the surface of the star. Now, the folks of Space Telescope loved it and said, oh, this is the place where it happened. So if you want to see a little cartoon of what we think may have happened, is that we have this hot spot that moved out, the material moved out, condensed, and the view from Earth blocked off the southern part of the star. I can remind you that there are these stars called our corona borealis stars, which are notorious producers of dust. And when they have a dust event, when they have a dust event, the magnitude on the star drops precipitously. I mean, much more substantially than with Betelgeuse. I mean, it could go down 3 to 4 to 5 magnitudes in a very short period of time. They're much faster. These are supergiants, but they're warmer than Betelgeuse. But the phenomenon of material moving outwards, cooling down, and dimming the star is well known and well documented in those stars. So what's going to happen next? The next minimum is due at the end of March. You see, here's a minimum I've marked here with the blue arrows. 25 days later, we saw the other minimum in February of 2020. And so it should be going right now, the end of March, which is, we're talking just about 2 months from now, 60 days from now. And the problem is it's getting brighter. These are the last observations were taken last week. It's getting brighter. We don't know what to say. we're going to find out. I should also mention these red stars marked on the optical light curve. They come from stereo. Stereo is one of a pair of Earth orbiting, well, they're Earth trailing, they're in the Earth's orbit, they're observing the sun. The idea is to have two satellites that observe the sun separated before the Earth's orbit and after the Earth in its orbit. And then they image the sun so that they can get a three-dimensional view of the structures and the activity that's happening. Stereo trails the Earth by about 2.5 months. And last year during the summer, we were able to use it. It has a wonderful 70-degree field of view CCD so that we could image the star field as well as comparison stars. And that filled in the little red dots, and we have them, they promise we're on the schedule. They're going to look at it again from May until August, maybe even late April through August of 2021. So stay tuned, we can follow it. I should also mention, we tried for one of the rovers on Mars, but it turns out that during July and August in Mars, there are dust storms. And when you have dust storms, it's very difficult to do, if not impossible to do photometry. Okay, so there are some additional thoughts. There's a lot of controversy right now and a lot of discussion and a lot of modeling ongoing about whether the photospheric temperature actually changed. Some of the photometry suggests that perhaps there was a remaining change in the temperature of the photosphere. And there we can look at the sun, because the solar CMEs have been known to evacuate the chromosphere way down to H alpha, even in the sun. And, you know, it may be that this material that left a cooling, a big cool region in the surface of the star. So maybe there's a cooler photosphere part. The other thing that's of interest is that the outflow that we saw came from the southeast, which is not from the rotation axis of the star. And that would be very interesting, because as you know, in the sun, we have fast winds where the rotation axis, where the magnetic field is open, and where it's very easy for material to leave. This was not from the rotation axis as far as we can tell. It appears to be symmetric as we came up with the Hubble aperture. This is also very similar to a recent preprint archive of VY Canis Majoris, which Roberta Humphrey posted, looking at bright knots that had been ejected from a similar supergiant, VY Canis Majoris, where they find that there are knots that can be attributed back to the surface of the star when there was a magnitude dip. And they came from all over. So it may be that we're seeing that there are these episodic ejections, and they perhaps can come from different parts of the star, not only from the rotational poles. So stay tuned. There's a lot of exciting things going on with Betelgeuse. Thank you.
So let's thank our speaker. It was a great talk. You can use your emoticons or the clap, please, so we can say the reactions.
You want me to stop
clap like this?
Okay.
So, do you have any questions? Please raise your hand so I can we can start asking questions.
Do you want me to stop the screen sharing or no?
Depends on
what the question is. Okay.
So is there any question? Yes, I have two hands. So Rassier, I'm sorry if you pronounced wrongly your name. Can you?
Yeah, hi, very fascinating talk. I just have a question that is just about basically the direction of this outflow from Betelgeuse. So I'm not actually sure that I understand, because during your talk you said that it's just coming from the southeast actually toward the Earth. And I was wondering, do we understand why it's, for example, it doesn't go from like a northeast or north actually west or whatever other directions? But at the end of your talk, you said that the outflow that we are seeing, today, they may come from different parts of the stars. Then the question is that why it's not so isotropic, like a wind that goes like in any directions, or like, getting more basically actually pronounced along the axis, rotational axis of a star itself. So sorry if you already answered this question, but it's not clear to me yet.
Oh, well, the rotational, I'm not sure I understand completely the question, but the rotational axis is roughly 50 degrees east of north. So what that means is that the poles should be in the direction of the northeast or the southwest. And our aperture for Hubble started in the southeast. So it went sort of 90 degrees from the polar axis. And when we looked at the distribution of the emission along the aperture, it looks symmetrical. It's not at one end as if it were coming from, because it might overlap a general region where the polar axis would be. So we're arguing, or it seemed to us that it's coming from the south, 90 degrees from the polar axis. One thing we're trying to do now is to get DDT time to follow up to see if there's indications of molecular plumes or something in that direction. We'll see. One problem has been this COVID thing, because all telescopes have closed down. So we went immediately in February. We headed off to every telescope we could think of, and even more, and everything closed down. So we may have missed an opportunity, but maybe there's another opportunity coming up this time. We'll see. Okay, I hope I answered that. Otherwise, I'll talk to you later if I didn't make myself clear.
Thank you so much. Thank you.
So one more question and let's go, or do we have to continue? I don't know. What do you think, Robert? Can I have one more question? Okay, Anna, you're next.
Yeah.
Hi, thanks, Andrea. It kind of builds up on where you left off answering this question. So I was really struck how much physics it seems like we can learn from this one event in Betelgeuse. And so it got me wondering, like, other than following it up just on Betelgeuse, what would it take to have similar campaign to identify similar events in other stars? Because presumably this might, maybe not to this magnitude, but I'm thinking the mechanism must be operating in other stars as well.
Yeah, so no. This is really interesting. First of all, Roberta Humphreys has an archive up, and I think it's in press on VY Canis Majoris, where they were looking with Hubble at these knots that have been sent out, have been ejected from the star, and they've traced them back because they can measure the velocity, and they can trace them back, and she traces them back to different parts of the star and different events. I mean, going back to the 1800s. When she could say, okay, this may have come from a particular time when the star was doing something strange, it was in a minimum or having some odd photometric behavior. And it's interesting for a lot of reasons. I mean, we tend to think that at least, well, first of all, we're judging from the sun, and the sun, of course, is a dwarf. It has a high gravity. It has a high corona, high temperatures, has a lot of flares, which Betelgeuse does not have. On the other hand, that's the only other star we can see in detail, and that's what we're learning from. And I also remind you that the sun, as a star, has a very weak magnetic field. As a matter of fact, the magnetic field is the same strength as Betelgeuse as a star. And we know that when we look at different parts of the sun, the field isn't 1 Gauss, but it can be kilogauss. So it's not implausible that there is remnant magnetic field that could be very strong in Betelgeuse that could help to propel this material. And I think right now it was sort of an accidental confluence of this outward motion as well as the minimum in the optical magnitude that brought on this ejection of material. There's a lot of discussion about what happened to this material. we said sort of obviously that, well, it must cool down, and maybe it cooled down and it made the star dim. Some people who have been observing it with iron 2 with CfA and some photometric studies say, no, 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 it's not really dust. We tend to think it's probably dust that caused this appearance. We have a paper right now that's in referee process with big paper because we had subsequent images of the star through February from Sphere. And we tend to think that it's probably most likely dust. But that paper should be coming out soon. I can't say anything about it, okay? but take a look at Roberta's paper that just arrived, and it's on the archive, and it suggests that you know, maybe the stars can lose material in a lot of directions. And this also is interesting because, you know, if it's from the pole, you're not going to change the angular momentum, but you can do all kinds of things when you're sending it off at the equator or at other parts of the star. So it's stay tuned. There may be more fun happening, and it's not behaving right now. I mean, it should be getting fainter. 90 days before a minimum, it should be getting fainter. It's now 60 days, and it's getting brighter. So we'll see. Is it going to be a supernova? Chances are, eventually, yes. Chances are not tomorrow. Don't do. When in February I went on one of the Twitter feeds, and somebody said, "I'm a theorist, and my calculations say it's going to blow up tonight." And then he wrote #run. Well, I'm not sure where you should run. I mean, remember, this happened 700 years ago. So stay tuned.
Okay, so if you want to continue talking with Andrea, please sign up in the one.
I'll sign up. Stop sharing.
Or stay at the end and we can continue if you want. Now is your turn, Robert. Thank you.
Okay, thank you for a good talk, and thank you, Tatiana, for handing over. Our next speaker today is Rachel Matson. She is an astronomer at the US Naval Observatory in DC, where she conducts observations for the Double Star program and manages the orbit catalog within the Washington Double Star database. Her research uses Speckle interferometry to detect double stars, and she'll be talking about Speckle imaging of exoplanets today. So I will hand over to Rachel. Thank you.
Great, thanks for having me. So yeah, as you just mentioned, talking about Speckle imaging of exoplanet host stars. And let's see, specifically talking today about stars that we have performed Speckle imaging of from missions like Kepler and TESS, also ground-based missions, but primarily transit missions where, as the animation is highlighting on the left, you have a planet crossing in front of the star, causing this dip in the light curve or a transit. And so the idea is when you see something like this, especially from space-based missions, you don't necessarily know what is causing that transit. You're hoping it's a planet, and a lot of times you have, it is, or you have good knowledge of what it is, but there's kind of no guarantee. And so there's various steps you have to go through to kind of prove that, to validate such a planet. And so the kind of artist depiction on the right is showing some of these kind of false planet scenarios. So what are some of the things that you could be seeing when you see a small transit like this? And so it could be indeed a planet crossing in front of a star, just like you hope to find. However, it could also be a brown dwarf or a low mass star. But it could also be the bottom scenarios you showed. These are actually binary stars or blended binary stars. And so basically the idea is that if you see a transit, you hope it's a planet, but it could be a lot of different things, specifically a nearby binary star or a grazing stellar binary. Also, when you do see a transit, the transit gives you the information about the size of the planet relative to the star. However, again, if you're seeing something that is not a planet that is transiting, you're not actually seeing a planet of the size that you're measuring. And then also, if there is extra light, something like a nearby binary, the the transit depth that you measure could actually be shallower than you expect because of excess light from the system. And so in order to validate the planets that are found, there are usually a series of steps shown by both, there we go. Kepler and TESS, for instance, have set up these whole extra kind of groups which go through and look at different levels, these just specifically for TESS, like the working groups, as I'm sure many of you are familiar with. And so one of those in particular is high resolution imaging. And the idea behind this is kind of illustrated in this series of images off to the right here, where you have what TESS would see because it has such large, roughly 20 arc-second pixels. And so that when you're actually looking at a star field, even if you are seeing these transits, it's really hard to tell which star that transit is actually happening around, or that potential transit. On the right here, you can see a seeing limited image. And so you can see there's actually several stars, including 3 fairly bright stars in that field. And so that's kind of one of the first stages to help validate these planets, is these seeing limited images. But even beyond that, sometimes there are extra stars kind of hiding in the pixels for either TESS or seeing limited. And so that's what the bottom row of that image is highlighting, is that using either speckle imaging on the left or adaptive optics at Keck on the right, that central star that you see in the seeing limited image is actually itself a binary star. And so the idea behind the high resolution imaging kind of follow-up process is to actually detect stars, whether they're actually bound binaries or just background stars, actually detect additional stars that are in the field of view that could be contributing extra light. And so this again helps eliminate these false positives, but then also characterize any contamination you are getting from extra stars in that field. And this is important, one, as I mentioned, for validating the planets, but even if you do have a planet going around a star, if that star in fact has a companion, then you're getting this excess light. And so you want to make sure that you're getting accurate parameters. And so you want to characterize that contamination and then be able to measure the true radius of the star and therefore then the planet in that case. And so as I kind of alluded to in the last one, there's different ways of doing this high resolution imaging, but I'm part of a group that uses Speckle imaging. And so this is a program that's been put together and run largely out of NASA Ames Research Center, but it's for validation and characterization of these exoplanets. In addition, Kepler, TESS, but also RV studies, ground-based work, kind of basically any exoplanet follow-up that's desired. But so this consists of, it's actually 3 speckle imaging cameras, and they are mounted permanently at GEMINI North and GEMINI South, which is kind of highlighted off to the right in those pictures. And then there is also a camera available for use at the WIYN 3.5 meter at Kitt Peak. And so our group does all of the imaging, as well as these are also available to the community if they wish to propose as well. But so this is kind of, these are the instruments that serve as the core of this speckle imaging follow-up program that we're conducting. And so just kind of either a refresher or a quick intro to speckle imaging. If you're not real familiar, speckle interferometry, same thing, just 2 different terms for it. But so speckle imaging basically takes a very short images, 40 to 60 millisecond images, which is represented on the left of this animation. And you see these speckles basically as the light is coming through the atmosphere. The turbulence of the atmosphere is spreading out the light. And so you see this pattern of speckles. Now you can see in the center of this animation, this is a normal integrated image. So when you expose for 10, 20, 30 minutes, however long in your object, you're building up all this light from the different speckles. And that's how you get that kind of central blob of light, that PSF shape that you're used to. However, on the left, you can see that we're just still taking these individual frames. We're not really, we take typically 1,000 of them, even more so if it's a bright star, if it's a faint star, but we're not actually adding them up. We're correlating them, especially in Fourier space, and detecting any kind of interference patterns that you get amongst these speckle patterns if there is a companion. And based on that, we can actually measure any separation and distance between these stars and reconstruct an image, which is shown here on the right. So what during that normal integrated, potentially seeing limited image, you don't see that companion, but with the speckle reconstructed image, you do there on the right. Here's just a visual of what that typically looks like. You can see all of our cameras have 2 different wavelengths that they operate at. So you get 2 channels of light. I'll actually highlight that here. So on the left, this is just highlighting the different parameters at WIYN and then at the GEMINI telescopes. And so you can see the typical magnitudes, can kind of see 14th to 17th magnitude, obviously a lot fainter at GEMINI based on the 8-meter size of the telescope. But then the diffraction limit, depending on which wavelength we use. Typically we use 562 and 832. So at WIYN, this is kind of a 0.04 to 0.06 arc second diffraction limit that we can actually measure companions down to that, and slightly even at smaller separations than the diffraction limit. And you can see at GEMINI pushing that to 0.02. And so the image on the right is then showing this. There's a reconstructed image right here in the corner, and you can see the companion that's been detected down here. And then this is the contrast curve. So the 5 sigma contrast limit curve for the 2 wavelengths that we observe in simultaneously. And so then you can see the contrast. And so at about 0.2, again, this is larger than the diffraction limit down here, but you can see that we can kind of get, again, depending on, this is a GEMINI image, so kind of 5 to 6, all the way out to about 8 delta magnitude contrast, so the contrast between the primary star or the target star and any companions that you're detecting. And so as I mentioned, this is a technique used to help validate various planets, because you can either look and see that there are no other nearby stars contaminating the light, potentially causing false positives. And so here's just a few recent papers, validation and characterization of several TOIs that have used this speckle imaging, primarily from GEMINI, but to help validate these planets. And I will just highlight on the top row here on the left, this is the contrast curve for this particular TOI 561, which is actually one of the oldest and most metal poor planetary systems. It's been looked at with TESS. And you can just see again, the contrast curve goes up to, in red, about 7 to 8 delta magnitudes, so where we would see any companions. And just highlight, AO was also done for this object. And you can see now they go out to that 8 to kind of 9 as well, but it's for a much kind of broader. They go all the way out to 4 arc seconds out here. However, if you're close in at about 0.2 arc seconds, this first dot, their contrast is just under 2, whereas Speckle, 0.2 is here, and our contrast is kind of 4 to 5 already. So it really helps you get that inner region, and this is working in the optical versus the infrared for AO. So it gives you kind of that close-in information, and again, just kind of different information as far as which companions you can detect. So just a couple other, as I mentioned, recent papers here. But to take a little bit of a pivot here is not only can you validate planets, but we're also detecting companions, and oftentimes bound companions to these stars. And so you can start to understand a little bit about, or at least explore, the relationship between exoplanets and stellar companions or binary systems. And so in 2017, Ferlin et al. Published a paper that basically published high resolution imaging for every KOI, so all the Kepler objects of interest, and found that about 30% of host stars have companions within 4 arc seconds. This was significant because the size of Kepler's pixels was 4 arc seconds. But either way, you're seeing they're detecting about 30% of stars having companions. Now for within 1 arc second, that was closer to about 10. But the point is there's still a lot of companions that could potentially contaminate what you're looking at. And so that's what the graph on the right here is showing, is that if you actually do have a planet, but you do have a stellar companion as well, is again, adding that contaminating light, and you also don't know which star that planet could be orbiting. And so the gray bars here are just what you would measure for the radius of the planet based on the transit. However, if you make this correction that, oh, the planet might actually be orbiting the primary star, then that's what these purple bars are here. And so you can see that you're actually very slightly shifting the planet radius distribution slightly to the right. And again, even more so if it actually orbits the secondary star, you're actually shifting it even more so significantly here. And so other papers in 2017 and 2018 looked at this similar and basically found that if you are measuring planetary radii, either without any kind of high resolution imaging in general, that you will underestimate the planet radius by 1.65 with no imaging, and on average with this high resolution imaging of 1.17%. And similar in 2018, saying that occurrence rates of small planets, especially less than 2 Earth radii, could be overestimated by as much as 50%. So again, just kind of highlighting why this is important and why we do need to understand whether or not these stars have companions and are binaries. Moving on to some more work that was actually done with various speckle images from both Kepler, which is on the left, and K2, which you can see on the right here. So the colored dots are actually actual observations that were made at GEMINI telescopes at the top panels and WIYN telescope at the bottom panel. But the idea here is actually some simulations were done where you took a sample of simulated stars and added companions to them at what we kind of consider the typical rate for solar nearby type companions from the Ragavan 2010 paper. And so then by adding these companions at the 46% rate, and then measuring which ones we could actually detect with speckle imaging, simulating that. And so those are basically any companions that are underneath the colored curves in these plots, which is magnitude difference on the left and the separation, the physical separation in arc seconds along the right. And so basically those colored lines are the contrast curves. But so what you can see is that when we actually added companions at 46%, we were able to simulate the recovery of planets roughly about kind of 12 to 15 to 17% at Gemini and about 5% at WIYN, which matched what our observations were, how many companions we were actually detecting. This is just because of where our detection space is. So that's one interesting thing that was done with these studies, is basically kind of overall, the number of companions that we detect around stars with exoplanets seems to be about the same, that kind of 40 to 50% that we see kind of typically overall for solar type stars. The other thing that was kind of interesting is there are both open and closed dots in these plots, and the open ones are ones where we actually simulated bound binaries. And the black or gray ones, solid points, were ones where you had basically nearby line of sight binaries. And you can see that especially Gemini, you detect a lot of those, but most of the inner ones, especially at these kind of 0.2 and 0.4 arc second separations, really were bound companions. So a lot of the stars, the companions being found with speckle imaging, a lot of them are bound. And so that's led to some interesting work trying to discover if is this overall 40 to 50% rate of binaries for exoplanet host stars and just for nearby solar type stars, do we actually see this kind of on different scales? And so in 2016, Krauss et al. Put out a paper that looked at Kepler Kepler KOIs, and then where they had found a companion and looked at kind of the separation, the distribution based on how far those companions were. And basically found that you see wider companions, but you don't see these close in stellar companions if the star is an exoplanet host. And so they basically said that then there is a suppression within 50 AU that you do not see close binaries if there's an exoplanet involved. And the plot on the left here is similar work that was done recently for TESS, TOIs, looked at with SOAR speckle imaging. So these are all Southern Hemisphere ones, but they kind of found this same idea. And so the red bars in this histogram are actually the binaries that they observed. And then this solid black line is where this typical 46% binary, that's where you would expect your distribution to look like. And you can see they didn't really see a whole lot in this inner region. And so that's what this dashed gray line is if you suppress these binaries, you have fewer close companions within about 46 AU. This is kind of basically what they said they're seeing. And so we have taken the speckle observations that we made now for the Northern Hemisphere for TESS at the WIYN telescope and performed a similar study to try to evaluate, are we seeing this suppression, this lack of kind of close stellar companions around exoplanet host stars? And so we observed 186 TOIs. Of those, about 45 companions were found, which is about 24%. However, speckle can detect a little bit wider companions, but really where our limits and our numbers are kind of best understood is within 1.2 arc seconds. So we concentrated on the inner region, and that's also where these are actually likely to be bound companions that we're looking at. And so you can see we had about 29 of them, which is plotted over here to the right. Again, delta magnitude versus separation. And about 80% of these were closer than 500 parsecs and 75% cooler than 7,000 Kelvin. So really mostly kind of solar type and a little bit less, but closer where with Kepler stars, they were much further away. So it's really hard to see those inner regions. So that's kind of why we wanted to use the TESS sample, is because these stars are closer. You can really kind of get into the inner 50 AU a lot better than you could for Kepler, just based on the separation, the distance of those stars. Okay, so this plot is taking, again, so you have delta magnitude, so the difference in magnitude between the host star and then any detected companions along the x-axis, and a mass ratio on the y-axis over here. And so the idea for each one of these is each line that you see in this plot is a primary star, is a host star that we looked at. And then just took a table of basically the Picot and Malmajek table of stellar characteristics for stars and said, okay, if we have, for instance, the bottom one is a G-type star because the line is yellow, what are the possible companions we could see just based on every spectral type that is cooler than that? And so that's what each one of these dots on this plot represent. And so you could have a mass ratio of 1, you would have basically an equal type star. You'd have a G primary with a G companion. That would be this first point over here, and that delta magnitude of approximately 0. However, as you have cooler and cooler companions, if you get down to an M star companion, you're really looking at delta magnitudes in the 4 to 6 range and kind of like a 0.5 mass ratio. So that's what this plot is showing, is basically the possible companions and which ones we can detect with Speckle imaging. And that's what this dashed gray line represents right here, is at a delta magnitude of about 6, that's kind of pushing the limits of Speckle at WIYN. And so these are the ones that we're sensitive to over on the left here. Then the black dots represent where the companions are that we actually detected. These are the ones that were actually observed. And so we use this plot to get an estimate of the secondary and specifically a mass ratio for the system. And so again, for this first TOI 462, a companion was detected with about a half 0.5 delta magnitude. And so based on that, we think that the companion is a similarly G-type star, just a little bit cooler than the primary. And so you can see how this was done for all of these stars. And this allowed us to then estimate a mass ratio for the system. And so we wanted to look at the distribution of mass ratios for this system. And so on the right, you can see this histogram. The ones with the stripes are essentially the ones within 1.2 arc seconds that we're concentrating on. The solid green is all of the detected companions. Basically, the idea is we're seeing a relatively uniform distribution, very much like what we would expect for solar type stars. There is a bit of a peak, it looks like, towards equal mass ratios, and it tails off mostly due to our detection limits. But we're seeing kind of what we expect, a fairly uniform mass ratio distribution. Plotting that versus separation, seeing a little bit of a closer separation, a little bit more towards those high mass ratio systems. But again, kind of very much what like we'd expect. However, if we actually plot the distribution and separation, and so this is just based on whatever angular separation we measured, and then using the distance from Gaia typically to get this projected separation in AU, what we would see. And so the blue bars here are detected companions. And then so there's a slight correction over here based on our contrast limits. But so this is the distribution that we actually observe. And with this red line is a Gaussian fit to that. And you can see that that peaks at about 100 AU. However, the expected companions, which are these yellow bars, pretty large error bars, but you can see that the distribution is kind of shifted inwards. And the peak for that is kind of around about 50 AU, which is where we expect that peak to be based on the Raghavan 2010 paper for solar type stars, nearby solar type stars. And so we're seeing, again, a shift in companions, but they're moving outwards. And so that's what this cumulative distribution plot right here is showing. So really, we're also seeing this kind of this fewer inner stellar companions, but they're actually seem to be pushed more outwards. So we're not sure if they're being suppressed or just kind of relocated outwards. We're also, as I mentioned, we have a lot of observations at GEMINI. And so we have a paper in the works by one of our collaborators who's doing this full study for the GEMINI sample. And this should help us get even more detail because there's more stars that have been observed, but also the detection limits, you're able to get even closer into the stars. And so with that, I'll just say that in my summary that high resolution Speckle imaging is helpful to validate planets, and also to get proper kind of accurate characteristics, I should say, accurate characteristics for both the planets and occurrence rates. But then also with discovering all these nearby stars, binary stars, we're able to start looking at whether or not binarity changes the exoplanet sample that we're seeing. And it looks like stellar mass ratios seem pretty consistent, but that we are seeing wider orbital separations in these samples than we do with samples that we don't obviously know that they have exoplanet companions.
Okay, thank you, Rachel. Yeah, so we've just like to thank the speakers today. I'll just do my applause here. And we have time for a quick question if anyone would like to raise their hand in the chat feature. We are running a little bit late on time, so if there are no questions, I would just remind everyone that the speakers have the online sessions that you can sign up to. So feel free to add your names to that. And yeah, with that, I will just say thank you to everyone. Thank you for joining. And we've been rearranging these sessions recently so that the next Stars and Planets one will be in 2 weeks. So that's just a reminder for everyone. And with that, I would like to thank everyone. Let's stop the record.